Und zwar geht es jetzt um das Thema Additive Manufacturing. Wir wechseln aber direkt auch ins Englische, denn unser nächster Experte kommt aus California und ich glaube mit dem Deutschen, I think the German, would you want to do it in German, Aaron? I mean, you can, you're free to if you want to. Nah, okay. Also, bleiben wir am Englischen. So we're going to stick to English, ladies and gentlemen. If you just happen to come along, welcome to the Siemens booth, welcome to the Thought Leaders Forum, and I'd like to ask everybody to come inside. Don't stand around out there. The action is all in here, so come inside and take a seat. We'll be talking about additive manufacturing, how it reshapes everything, and that means reimagining products, retooling manufacturing, and how to rethink business. And Aaron Frankel, ladies and gentlemen, will make you change the way you think. So please give him a big round of applause. Here he is.
Thank you, sir. Thank you, Chris. Hello, everyone, and welcome to Hanover Fair. It's my pleasure to be here to talk about additive manufacturing. So at Siemens, we believe in creating new ways to design and to produce better products. And the way we do this is we combine digitalization and additive manufacturing so that we can take ideas in our heads, turn them into digital models that we then have the freedom and the flexibility to manipulate the way we need to, optimize them till they're just perfect, and then turn them into atoms. But in order to take advantage of this technology, we believe that designers and engineers and manufacturers, we all need to think differently. We need to reconsider how we design in order to unlock the power of this new technology. When you think differently, you can achieve designs that look like this. This is a significant product. This is something that can be used in fuel refinement. It's a high temperature burner. And what it does is it burns messy fuels left over from the refinement process at extremely high temperatures to be able to extract the hydrogen. The temperatures are so hot that they're hotter than the melting point of the metal of this part. The way that you keep it cool is to change the way we think about design and design for function. And we're able to use modeling tools, CFD, computer-aided engineering tools, as well as design space exploration tools to be able to optimize the performance of this system so we can run coolant through this product and keep it cool while we burn the fuel. We also have to think about performance differently. We can optimize performance. What you're looking at here are two examples of the same part that perform the same job. This is a lever on an aircraft. What it does is it connects the actuation of the pilot's joystick to the elevators on the back of the aircraft that can control its lift. And what we've done here is we've used generative design tools, tools that allow designers to input the design goals of a problem and then let the software calculate the shape. And the software generated a shape that performs the same job as the original design. It's just as strong, but it happens to be 15% lighter. But it's difficult to be able to make this shape using conventional manufacturing. Additive manufacturing is the technology that will enable these shapes to come to life. Another way we have to change the way we think about design is designing for mass customization or individualization or personalization, like this example here. This is a surgical cutting guide. It's used in joint replacement therapies in hospitals today. And what's significant about this is we've been able to create a digital twin of a person's anatomy, in this case, the knee, and we use that digital model to give us the inner shape of the cutting guide so that it perfectly matches the patient during the operation. This cutting guide's job is to help the surgeon keep the cutting instrument in the proper location. It removes risk and increases consistency of the operation. Just some examples of the power of additive manufacturing when we change our design and start to think differently of what's possible. But in order to take advantage of these technologies or this power, we need to retool our production capabilities. We need to introduce additive manufacturing technologies that will allow us to change the way we think about design. And there's a number of technologies at Siemens that we're working with many of the industry leaders in printing OEM printer capabilities to be able to drive. And these are some examples of 4 of the primary technologies. Powder bed fusion is a technology that uses a very fine laser and very fine powder. The powder can be metal, ceramic, plastic, polymers, and we basically melt the metal layer by layer as we grow the part. We have very fine control over this laser, and that control enables us to make the shapes that you see on the interior of that burner. This is that gas burner tip that I mentioned earlier, that heat exchanger. Notice the interior shapes. You would never be able to produce this using conventional manufacturing processes. Pretty powerful. Another technology is jetting. In order to unleash the power of additive manufacturing, we need to be able to produce parts economically and at large volumes. Hewlett-Packard is pioneering technology for jetting with the new printer that they recently announced last year. And we're working very closely with HP to unlock its power. This gear was printed using the HP printer, one of the first versions. If you talk to HP, they'll tell you that with that printer, you can produce 55,000 of these parts as cost effectively as you could use injection molding. So now we're able to produce large volumes, large quantities of parts to begin to replace traditional tooling, which has long lead times and can be quite expensive. Another technology is direct energy deposition. And what it allows us to do is take a powder nozzle that blows metal powder in a direction and then hits the powder with a laser beam. And we can control that powder nozzle in 5 axes. And we can actually put that on a machine tool that also has CNC machining. This is something that DMG Mori has pioneered, and we've worked very closely with DMG Mori to help be able to drive these types of tools. Now, what that enables us to do is create very complicated shapes in multi-axes, but then also bring in a CNC cutting tool and finely machine this geometry to the precise shape and the surface finish that we're looking for. And we don't have to take this part off to another machine in order to do those operations. We can do them all together on one machine. You can see an application of this in marine, in aerospace, and in energy. I think another interesting element of this technology is we can also begin to fuse multiple materials together in the same part, which unlocks a whole new capability. And then lastly, another example is this part. This is a material extrusion example, something that we've worked very closely with Stratasys on. And Stratasys has equipped a robot, a multi-axis robot, with an extrusion head that can extrude carbon-reinforced nylon. It's a composite. That robot's controlled with a Siemens Cinemeric controller, and it's programmed using our software. And what's significant about it is now we're able to automate the production of composites. We can get the repeatability and the quality that we're looking to achieve. And composites are important because they allow us to replace maybe metal parts that are much lighter. Interesting applications in aerospace, for example. And when you combine this new way of thinking for design and these new technologies for production, we can unlock new business models, new ways of doing business. We can begin to think about printing on demand in the location where we need our parts. And this is significant because now we can start to eliminate physical inventory and replace it with digital inventory, removing the complexities of logistics, for example. We can design specifically for our target consumer using the individualization and personalization capabilities, as well as shrink the innovation cycle. If we no longer need to rely on tooling, for example, during the prototype process, or castings for prototyping, we eliminate the long lead times, and we're able to now iterate and test on real physical parts and do it much faster than we could have ever imagined, which is going to help us increase the performance of our products much more quickly. But there's a big problem. There's a big challenge, and the challenge is a disconnected process chain. Many companies that are pioneering the application of this technology today face a lot of challenges, and the challenges are in a disconnected process chain on the software and design side, where we have to use many different applications from different systems, as well as a disconnected production environment, where we have 3D printing, for example, on an island, someplace outside the production environment. And so what we're doing at Siemens is we're connecting this entire process. We're adding tools into our digital enterprise suite on the software side and on the hardware side to be able to connect together those workflows. In the PLM space, we've added new design capabilities into our system so that now we can create these organic shapes and assist designers in rethinking their products. We have simulation tools that allow us to analyze the performance of our designs as well as how we're going to produce them. We have the ability to prepare our parts and our designs to be printed on these different technologies. In the area of totally integrated automation, we have technology, automation tools that we can load into the cabinets of these machines so that we know we can use these machines anywhere on the planet and they will perform consistently. And we have the ability to digitally connect these machines into our networks and production so that we can deliver information and collect information off those machines to help us optimize our designs. And we also provide the capabilities to manage all of the manufacturing operations in the production environment so that we can hit our schedules, we know where our orders are, we know what our operators need to do, and we're always delivering the right information when and where we need it. And lastly, we recognize there's a lot to learn. And in order for us to truly industrialize this technology, we need to be able to tap into the resources that are available to us in every industry, between designers and manufacturers and institutes and students, young engineers, experienced engineers. And so we're building a platform that allows us to co-innovate, where we can collaborate online, share information, co-create designs, and we're adding tools into this environment so that people have greater access to the technology and the information. Thank you very much for visiting us today. If you would like more information, please feel free to come visit us. The Additive Manufacturing Highlight Cube is right over here. We've got a lot of great examples, and we've got a great team of people who would love to talk to you if you have any questions. Thanks for coming.